All right, Module 7, we are continuing on with the polynomial functions. If you look at 7.1, it is a summary of the graphing techniques. So what we talked about previously, how the graph can be translated or shrunk or stretched or even reflected. So this summary right here is, you should already have it in your notes. And then we also have some graphs, and then it tells you if the leading coefficient is positive or negative. And then it just has the different graphs, what they're doing. And it's an example of what is going on, the shift of the graph. This one is actually a reflection. So there will be homework questions on this that are on the test, and we will look at it at the end. These are just some more examples that you can look at. And then it says just concepts to consider at the very end. Turning points, a polynomial function of degree n has at most n minus 1 turning points. So let me highlight this. With at least one turning point between each pair of successive zeros. Behavior of zeros: if an equation is in factored form, then if the multiplicity of the factor is odd, the graph will cross the x-axis. If it is even, it will touch the x-axis and return to the same direction that it came from. If it is equal to or greater than 2, it will flatten at that point. So that is useful information there. And then in behavior of graphs of polynomial functions, there is an example. We have the polynomial function, and then we have it factored. And it just talks about this polynomial, so you can look at that. The graph, and another example at the end. For 7.2, we are looking at the intermediate value theorem. It says if f of x is a polynomial function with only real coefficients, and if for real numbers a and b, the values of fa and f of b are opposite in sign, then there exists at least one real zero between a and b. So a lot of stuff going on in this theorem. If you look at the example below, it does explain the theorem. So we have that f of x equals 2x squared minus 7x plus 4. So basically what that theorem is saying, if you look at this example, it says use the intermediate value theorem to show that each polynomial function has a real zero between the numbers given. So it gives us the polynomial function, and then it tells us that we're looking between the numbers 2 and 3. So we're going to plug those numbers in. We've got f of 2, and we do the math, it ends up equaling -2. And then f of 3 equals 1. So it says that signs have changed, therefore there is a zero between 2 and 3. So it says up here, if for real numbers a and b, the values of f of a and f of b are opposite in sign, then there is at least one real zero. So the f of 2 equals -2, so we know that there is a zero between 2 and 3. The boundedness theorem says let f of x be a polynomial function of degree where n is greater than or equal to 1 with real coefficients and with a positive leading coefficient. Suppose f of x is divided synthetically by x minus c. So if c is greater than 0 and all numbers in the bottom row of the synthetic division are non-negative, then f of x has no 0 greater than c. If c is less than 0 and the numbers in the bottom row of the synthetic division alternate in sign, with 0 considered positive or negative as needed, then f of x has no 0 less than c. So here is an example. It says show that the real zeros of f of x equals, and they give us a polynomial, satisfy these conditions. So a is no real zeros greater than 1. So we do synthetic division, and all of the numbers in the last row are non-negative and 1 greater than 0. So there is no real 0 greater than 1. So this is what that theorem is saying for that. And then no real 0 is less than -2. And then if we do synthetic division, our bottom row, it says all the numbers in the last row alternate in sign. So we have positive, negative, and -2 is less than 0. So f of x has no real 0 less than -2. Okay, 7.3 is the transform rational equations. So a rational function is a function of the form where we have two polynomials, one divided by the other. So p of x divided by q of x. Q of x cannot equal 0. So on the notes, there is the summary of the graphing techniques that you can use. The simplest form of rational functions, 1 over x or 1 over x squared. And then we have some graphs that we are looking at. So just go through and look at some of these graphs. And you can either even play around with them on your calculator. And then 7.4 is the last one. It's going to be graphing a rational function. So remember, we've got two polynomials, one dividing the other. Asymptotes. An asymptote is a value that you get closer and closer to but never quite reach. So your graph is going to continue to get closer and closer to some point or a line, and it's never going to touch it. So it approaches but never touches. So let me highlight this. I'm going to say, so it is a horizontal, vertical, or oblique slanted line that a graph approaches but never touches. So we talk about vertical asymptotes, horizontal, and then oblique or slanted asymptotes. And then there are some examples down here. So if you look at these lines, this purple dotted line, these are the asymptotes. So this is what the graph is going to approach, but it doesn't matter how far you get, it will never touch those lines. So there's lots of examples down here. There are some graphing techniques for rational functions. So let me look at these. So there are some graphing techniques for rational functions and different steps. So we will be looking at these steps whenever I go through the homework. And there are examples, of course, down here. All right, so let me go ahead and pull up the homework. Okay, so homework for 7.1. Remember, I'm only going to go over the questions that you need to look out for on the test. So I'm not going to go over number 1. Number 2, I will do. It says sketch the graph of the polynomial function f of x equals, and then we've got negative x plus 1 cubed plus 2. Determine the largest open intervals of the domain for which the function is increasing or decreasing. Okay, so we know that our polynomial has a cubed. So our graph is probably going to be something like this or like this. It is going to have 2 turning points. Remember, our notes say that a polynomial function of degree n has at most n minus 1 turning points. So cubed, we have x cubed, so we know that there's going to be 2 turning points in our graph. So this is going to be 7.1, number 2, and we are going to graph f of x equals negative x plus 1 cubed plus 2. So if you look at your summary, I think it's up here, this will tell you everything that you need to know. We know that we have a negative f of x, so it's going to be reflected across our x-axis. We also have some shifts going on, or translations. So we have x plus 1, so we're going to be going to the left. And then at the end we have plus 2, so we're going to be going up. Okay. So I'm going to make a table for x and y, and I'm going to find some points that are going to be on our graph. So I'm going to start with x equals 0. So for f of 0, I get negative 0 plus 1 cubed plus 2. 0 plus 1 is just 1. 1 cubed is 1. But we have our negative, so we have negative 1 plus 2 equals positive 1. Okay, so I've got 0, 1 as 1 point. Let's try where x equals 1. So I've got negative 1 plus 1 cubed plus 2. 1 plus 1 is 2. 2 cubed is 8. And then we have our negative that we're bringing. Negative 8 plus 2 equals negative 6. Okay. Let's look at x equals negative 1. So f of negative 1 gives us negative, and then we've got negative 1 plus 1 cubed plus 2. So I've got 0 cubed is 0 plus 2 gives us a positive 2. So let's look at our graph. Now I know that we are going to be using this. And I'm going to just go ahead. I've got 0, 1. Actually, let me start with -1, 2, 0, 1. -1. I'm sorry, I did that one. 1, -6. And I'm going to need another point over here. So let's do where x equals -2. So f of -2 equals, I've got negative and then -2 plus 1 cubed plus 2. So -2 and +1, I have -1 cubed. So negative, positive, negative, I end up with -1 and then plus 2. This is a positive, so 1 plus 2 equals 3. So x equals -2, y equals -3. I'm sorry, +3. All right, save, check. Great. So you do need 4 points to graph this in Pearson. Select the correct choice below, and if necessary, fill in the answer box to complete your choice. It says the function is increasing or the function is not increasing. So we need to see where our function is increasing at. So if we're reading it like a book left to right, we're coming down and then it looks like it stays flat and then it goes down. So it does not look like it's increasing. All right. The function is decreasing though. So we are decreasing, so infinitely. So it's going to be -infinity to infinity. All right. So there is a question like that on the test. We're not going to do number 3. Number 4. Describe the end behavior of the graph of the polynomial function. All right, so number 4. Describe the end behavior of the graph. So f of x equals 5x to the 5th plus 3x cubed minus 4x plus 2. So this is our leading coefficient, so this is what we're going to be looking at. So a equals 5. So 5 is greater than 0. Our term is odd. So if we look at our notes for our graphing techniques, we have that a is greater than 0. So it's going to be a vertical stretching of our graph. So if we look at our notes, it does have some examples, the end behaviors of graphs, and we want to look where x is x to the 5th. It is positive, so it's going to follow this graph over here. So what our graph is going to look like is this. So our end pieces is going to be like letter D. All right, let me look at, I'm not going to look at 5. I'm not going to look at 6. Let's look at number 7. It says graph the polynomial function, factor first if the expression is not in factored form. All right, so f of x equals x cubed plus 9x squared plus 11x minus 21. We do need to factor it, so we're going to use synthetic division. So I'm just going to start with 1. They don't give this to us, but I'm going to just try it out. So I've got 1 for x cubed, 9 for x squared, 11, and then negative 21. So remember, our 1 comes down. 1 times 1 is just 1. 9 and 1 is 10. 10 times 1 is 10. 10 and 11 is 21. And then, woohoo, it works out. So I can use x equals 1. So our factor would be x minus 1. And so I've got x minus 1, and then I've got x squared plus 10x plus 21. And now I can factor this. So x minus 1, and then I've got x and x. And I need to multiply, I need to have terms over here that multiply together to get to 21, and then also can add to get to 10. So 7 and 3 is the first thing that comes to mind. 7 and 3 multiplied together gives you 21. This is going to be positive because 7x and then 3x total to 10x to get our middle term. So we have factored it. So x equals 1, x equals negative 7, and then x equals negative 3. So that means at these places where x equals these numbers, y equals 0. So that means that the graph is going to touch our y where x equals 1, x equals negative 7, and x equals negative 3. So we do need one more point. I'm going to make our table. So I have 1, 0, negative 7, 0, and negative 3, 0. Let's look at where x equals negative 2. So f of negative 2 equals, and I've got negative 2 cubed plus 9 times negative 2 squared plus 11 times negative 2 minus 21. All right, so negative 2 times negative 2 times negative 2 gives us a negative 8. Negative 2 times negative 2 is a positive 4. 4 times 9 is 36. 11 times negative 2 is negative 22. And then we've got minus 21. So negative 2, negative 15 took a turn. So let's try to graph some of our points. It is cubed, so I'm going to be using our cubic tool. So I've got 1, 0. I've got negative 7, 0. I've got negative 2, and negative 15. Oh, it goes over here. Negative 2, negative 15. And then also negative 3, 0. Alright, so save, check, woohoo. Alright, and then I'm going to do number 8 as well. So graph the polynomial function, factor first if the expression is not in factored form. So, multiple choice, we've got 8. I've got f of x equals x squared, and then x minus 3, x plus 2 squared. So I'm going to set these equal to 0. X squared equals 0. Okay, so x equals 0, and then I've got x minus 3 equals 0, so x equals 3. X plus 2 times x plus 2. So x plus 2 equals 0, x equals negative 2. Alright, so I've got 3 points that I can look at. I have 0, 0, 3, 0, and then negative 2, 0. So let's look at our graphs. We know it's going through the origin. So let me make this one bigger. So we've got 0, 0, we've got 1, 2, 3, 0, and then also negative 2, 0. Okay, let's look at B. Okay, 0, 0, negative 2, so not B. For C, got 0, 0. Okay, so we don't have 3, 0, we don't have negative 2, 0. Okay, so not C. And then D, 0, 0, negative 2, 0, and then 3, 0. So it's either A or D. So I need to find one more point. Let's look for x equals 1. So f of 1 equals 1 squared, 1 minus 3, and then 1 plus 2 squared. So that just gives me 1 times 1 minus 3 is negative 2 times, and then 1 plus 2 is 3 squared, which is 9. So 1 times negative 2 is negative 2. Negative 2 times 9 gives me negative 18. So where x is 1, y equals negative 18. So I think that D is the one that is going down over here. So for x is 1, y is negative 18. And that looks about right because this y is negative 100. So if we break it up like 20, 40, 60, 80, 100, so this would be about around negative 18. So I think it is letter D. Awesome. Okay. I'm not going to look at the rest of these. I'm going to look at 7.2 next. Okay, 7.2. Okay, 7.2 is super short. I'm not going to look at any of these questions. I'm going to go straight to 7.3. All right, 7.3. I am going to look at number 1. There is a question like this on your test. It says, explain how the graph of the function f of x equals 4 over x can be obtained from the graph of y equals 1 over x. Then graph f and give the domain and range and determine the largest open intervals of the domain. So let's look at our 7.3 notes. If you look at these notes, we are looking at the rational functions. Let me zoom out. And it has a summary of the graphing techniques on this first page. So if we have our parent graph is y equals 1 over x. And the function that we're looking at is f of x equals 4 over x. So if we were to look at this is 7.3, number 1. F of x equals 4 over x. So this can also be written, if you want it to be very similar to your parent graph, it can be 4 times 1 over x. So in this case, 4 is going to be our a. So a times f of x, so we're looking at this left side, a is greater than 1, so it is a vertical stretch of our parent graph. So it says to obtain the graph of f, it's going to stretch the graph of y equals 1 over x vertically, because a is greater than 1, by a factor of 4. Because a equals 4. So now we are going to graph our function. Let's look at our parent graph for f of x equals 1 over x. So this is our parent graph, so we know it's going to be either B or C because it is following that parent graph. It is just being stretched vertically. So I'm thinking it's going to be B. All right, great. Now for our domain, it is coming from negative infinity to infinity, but if you look, there is, like, it is approaching the y-axis. So it's never going to touch, but it is approaching there. So our intervals would be negative infinity. Oopsie, I don't want to do that. So negative infinity to 0. And then also it's going to be 0 to infinity. Okay. And then our range, similarly, our graph is approaching the x-axis, but it never touches it. So it's going to be this same interval. I've got negative infinity, comma, 0, and then 0, comma, infinity. All right. And then it says the function is increasing, so it looks like it's coming from over here and it's going down, and then again it's coming down and over. So it doesn't look like it is increasing, but it is decreasing. So it decreases from negative infinity to 0. And I'm going to use a comma because this isn't the same as our range. We're not unioning it. We're just basically saying it's decreasing from here and from 0 to infinity. Alrighty. I'm going to look at number 2 as well. It says explain how the graph of the function f of x equals 1 over x plus 5 can be obtained from the graph of y equals 1 over x. So very similar to what we just did. I'm just going to do the graph part. I'm not going to go through everything. So we have 1 over x plus 5. So I've got a vertical shift or a translation of 5. So to obtain, shift the graph of y up 5 units. Alright, and then pick the graph. So it's the same graph that we were looking at for 1 over x, but it is just being shifted up. So now instead of approaching our x-axis, it's going to be approaching it's going to be approaching for y equals 5. So that horizontal line up here. So all of these, so this one, it's not D because this one is going down. C, it's not A because this one looks like it shifted to the left. It's not 16 because this one has been shifted to the right. So it has to be C because it's still going to our y-axis, but instead of going to the x-axis, it has gone up 5. Alright, I'm not going to go over the domain and the range. I think you can get that part. Number 3, I'm not going to look at that one. Alright. So that is it for 7.3. The rest of the test questions come from 7. So 7.4, I'm going to look at number 2. It says, give the equations of any vertical, horizontal, or oblique asymptotes for the graph of the rational function. And they give us that f of x equals x squared minus 5 divided by x plus 5. Alright, so if you look at your notes, it has the different steps in order to find your vertical and horizontal asymptotes. So starting with our vertical asymptotes, we are going to solve for 0. So our denominator, x plus 5, we are going to set this equal to 0. So I'm going to say vertical asymptotes, x plus 5 equals 0, so x equals negative 5. For our horizontal, we have x squared. Since it is greater than x, there are no horizontal asymptotes. For our oblique asymptotes, we are going to divide. So I'm going to use synthetic division. I've got x squared, 1x squared. I don't have an x, so that's going to be 0. And then I have negative 5. And I'm going to use negative 5 to divide. So 1 is coming down. 1 times negative 5 is negative 5 plus 0 just gives us negative 5. Negative 5 times negative 5 is going to give a positive 25. Minus 5 gives us a positive 20. Okay, so for our asymptote, I'm only using this because this is our remainder, remember? So I've got x minus 5. So y equals x minus 5, and that is going to be the line that we're looking at. So the equation of the vertical asymptote, x equals negative 5. For the horizontal, there is none. The oblique, y equals x minus 5. And that is all that they are asking for. This one, there is going to be, for question 3, there is going to be a horizontal asymptote because we have x squared on top and x squared on the bottom. So there will be a horizontal asymptote. The only reason there wasn't one here is because x squared was greater than the x that we had on the bottom, so there wasn't a horizontal. I'm not going to go over question 3. Number 5 I will look at. It says graph the rational function f of x equals x plus 4 over x plus 7. So number 5. Graph f of x equals x plus 4 over x plus 7. So those of you that have a calculator, this is easier for you because you can just put it into the calculator and graph. For those that do not have a calculator, you're going to want to follow the rules from your notes, the translations and the shifts. Find your asymptotes. So let's start by looking at our vertical. I've got x plus 7 equals 0, so x equals negative 7. The horizontal, there will be a horizontal asymptote. So since these are equal, they are both x, then y equals 1 is the horizontal asymptote. Y equals 1. So let's go ahead and look. We have a vertical asymptote at x equals negative 7. So that means we're looking over here, which kind of looks like it could be A or D. I don't think it's C or B. Let's zoom in. So it's either A or D. Our vertical asymptote is x equals negative 7, which is over here, but y equals 1 for our horizontal, which is up here. D is incorrect because it looks like it has y equals negative 1, so it is A. Awesome. So there is a question like that on the test. And then the last question is going to be one like this. So you will need to sketch the graph of this rational function